Okay. If you wouldn't mind introducing yourself at the beginning so that we know the camera.
Okay. I'm Mark Hughes from the Advanced Technology Institute, and I'm going to give a very brief introduction to quantum computers, which is something that I work on. So these are the learning outcomes. Hopefully by the end of this, you'll be familiar with the concepts of quantum superposition and wave functions. And you'll also know the difference between a quantum computer and a classical computer, which are the laptops and phones that we use every day. And you should be able to understand the advantages of quantum computers over classical computers. So, firstly, I'm going to talk about waves, because waves are really important for quantum systems. So this animation is showing what you might see in something called a ripple tank. You might have used them at school. All it is just a shallow tank of water with an oscillator in to make waves in the water, and then you can just project it and see what the waves are doing. So in this ripple tank, we've got a screen with two holes in it. So we have two sources of waves, and these diverge and then they interfere. So where you have the crest of a wave meeting the crest of another wave, they add up together and you get constructive interference and you get these bright bands. And then where the crest of a wave meets the trough of another wave, they just cancel each other out and you get nothing. So if we look at the intensity of the waves where they hit this screen, you'll see a series of bright and dark fringes, which is known as an interference pattern. So when you see an interference pattern from two sources of something, you know you're dealing with waves. It has to be something wavy. So what if we tried a similar experiment, except instead of waves, we're going to use tennis balls. So let's imagine we've got a tennis ball machine, and we're going to fire tennis balls at a wall with two gaps in it. And then they're going to hit this screen, and we're going to look where they hit this screen. And let's say we do something like put chalk or paint on the tennis balls so that we know where they're going to hit. So what kind of pattern do you think these tennis balls are going to make on the screen?
On that screen.
Yeah, what would it be? Would it be a lot of fringes, or a few?
Confined to one place.
In one place?
Within the gap area.
Yeah. Two places, you think? Yeah. Obviously we'd see it in two places. The tennis balls can't interfere with each other. Tennis ball can go through one gap or the other gap. So it's going to hit here or it's going to hit here. So when we see the slit pattern, the same pattern as the slits, we know we're dealing with a lump of something. It's something solid that's not going to interfere with itself. Now, let's try the same experiment again. But instead of a tennis ball machine, we're going to have some imaginary particle gun, and it can fire particles of light, which are known as photons, particles of electricity, which are known as electrons, or particles of stuff, which are atoms or molecules. And again, we're going to fire them at double slit, something with two holes in it. And then we're going to look here on this screen what pattern they make. And we're going to fire them one at a time at this gap. So what pattern do you think they'd make on this screen? It'd be the same as the tennis ball? No? The same as the waves? Something different? Something in between. What we get is exactly the same as the waves. We get an interference pattern. So this is really interesting. We're firing lumps of something, and we're firing them one at a time, but it's making something which shows we've definitely got a wave, not a lump of something. So what's going on here? What does this mean? What it must mean is that these particles, as we fire them, they must go through both slits at the same time. To get an interference pattern, it has to go through both slits to be able to interfere with itself. So these particles are in two places at once. And this is where we get the concept of quantum superposition, being in two places at once. And we also know it's a wave. We've got an interference pattern, which we know means we're dealing with a wave, not a lump of something. So we call the waviness property of these particles its wave function. Now let's try the same experiment again. It's exactly the same. We're going to fire particles one at a time, but we're going to put some kind of detector in front of those gaps, those slits, and we're going to sit and wait and see when the particle goes past each slit, so we can tell which slit it's actually gone through. So what pattern do you think we'd get now? Be the same as before? Different? Any guess? Actually, what we get is the same as the tennis ball. We've changed it. So just by looking which slit the particles actually go through, we stopped this waviness property of particles. So now they're behaving like tennis balls. They're like a lump of something, just from measuring it. So it's this measurement which causes what we call the wave function collapse. The waviness property of the particles has disappeared. And also the superposition has disappeared. Instead of going through both slits at the same time, it's only going through one. It's going that way or that way. Now, I'll just go over briefly how classical computers crunch numbers. So the computer, your laptop, your phone, the data in there is represented by ones and zeros. And these ones and zeros are represented by a voltage or no voltage, or in an optical fibre that is used in the internet, could be light or no light, or in a computer hard drive it could be a magnetic field pointing up or down. And the crunching of those numbers, the processing, is done using gates. So this is a typical gate, there's lots of gates. It's called an AND gate. The output gives you a 1 only if both inputs are 1. If it's 1, 0, 0 and 1, 0 and 0, you get a 0 on the output. And then we can connect a load of these up in a particular way and we get a simple adder. And if we scale this up a lot more, we get the microchips in your computer, your laptop, your phone. So on a very basic level, that is how classical computers crunch numbers. But there are some problems that are really difficult for classical computers to do, because there are certain problems where you can't just work out the solution. You need to try every possible solution until you find one that works. Some examples of this is finding the prime factor of a number, so that's finding two prime numbers that multiply together to give the number that you want, or searching an unsorted database, or finding the quickest route through a network, or working out how proteins fold in biological problems. So this is a big number, quite a big number, a few hundred digits. So if we put this number into the most powerful computer in the world and told it, find me two prime numbers that multiply together to give this number, how long do you think it would take? Any idea?
Day.
No?
A year.
No. It would take longer than the age of the universe, much, much longer. It would take many, many times the age of the universe to compute that number. So this is really important because it's this type of problem which underpins the secure internet. internet connection that you use when you do your internet banking. It's the difficulty of that problem which makes that secure. So how do quantum computers crunch numbers? Well, the data in quantum computers is represented by systems, quantum systems, that are put into a quantum superposition. And these make what are called the qubits, the bits of that quantum computer. Now, many different phenomena can be put into a quantum superposition. For example, electrons have a property called spin. So an electron can be spinning clockwise, or it can be spinning anti-clockwise. And we can put an electron into a quantum superposition where it is spinning clockwise and anti-clockwise at the same time. Also, electrons bound to an atom have to exist in certain well-defined energies called energy levels, and an electron can be put into a superposition where it is in two energy levels at the same time. Similarly, a photon can be polarized vertically or horizontally, and it can be put into a superposition where it's polarized vertically and horizontally at the same time. So the processing in quantum computers is also done with gates. They're not the same gates that you get in classical computers, but it's the same principle. We have some way of controlling the interaction between the qubits that make up our quantum computer. So these qubits in our quantum computer, because they're in a quantum superposition, they don't just represent 1 or a 0. They represent a 1 and a 0 at the same time. And this is fundamentally what gives quantum computers their power, because it means as long as we don't measure the qubits in our quantum computer, it can compute every single possible solution to the problem that we give it at the same time. And then once it's computed the problem, we measure it, and the wave function collapses and decides what state it's actually in. But it's done that computation all at once, whereas a classical computer will have to go through every possible solution. So the potential of this is massive. They can be much, much faster than classical computers for certain problems. So why has no one built a quantum computer yet? Well, quantum superpositions are extremely delicate. These superpositions of states can be easily affected by very tiny disturbances in the environment. So in order to keep these quantum superpositions, we need to isolate the qubits from their environment to stop the environment kind of leaking in and causing a wave function collapse. But we also need to read them out to get the solution to the problem that we give them. So this is a bit of a trade-off, because to read them out, we need the environment to interact with them. So this is a major problem for building a quantum computer. We also need to address the qubits. We need to set them up with the problem we're going to give them and put them in a superposition. And we also need to control them, the gates, to control the interactions between them. This is also extremely difficult. So actually, some people have built very, very simple quantum computers so far, just with a few qubits. And the biggest problem that's been done so far with these really simple quantum computers is factoring 21. So they found the factors of 21. But that's because of these really difficult problems that we have problems scaling it up. But each qubit that you add to your quantum computer, you double its power. So if we can overcome these problems, then we'll be able to build a very powerful quantum computer.